hydrogen might look like. So we've seen that hydrogen are perfectly happy in pairs. So you might imagine that in a container you could have, these hydrogen pairs kind of all floating around, being perfectly happy in their own world. And whenever you have a small number of atoms covalently bonded to each other, we give that a name. We call these little peanuts here molecules. So an atom of hydrogen would be just one hydrogen. A molecule of hydrogen would be two hydrogens bonded together. In this case it's two, depending on which element we're talking about. So we see that the structure of hydrogen is what we call molecular, and these molecules that have a small number of atoms in them, we call these simple molecules, since they have a small number of atoms to each other. And it turns out that there's also some attraction between the molecules, but this attraction is very weak. Sometimes called London forces or Van Waals forces, but we won't go into that for now. So this weak attraction between them causes them to have a very low boiling and melting point. That's why hydrogen exists as a gas at room temperature. Likewise, we can look at the structure of chlorine. Chlorine is gonna form diatomic molecules like that, kind of floating around in space. They're all perfectly happy with each other. So we have inside the chlorine, we have strong covalent bonds inside the chlorine molecules right there. So strong covalent bonds. Whereas in between the chlorine molecules, we have this weak force. Weak forces between them because they're strong inside because they're sharing electrons, whereas outside of them, they're not really concerned with each other because they're perfectly happy. I mean, they're perfectly happy in pairs. They don't need to get extra electrons from someone else. So there's this really weak force between them, this weak London or Van Waals force, and hence they also have a low melting or boiling point. That's why chlorine is a gas at room temperature. And we see the same situation here with oxygen. With oxygen, and there are strong bonds. Oops, this is a double bond, so it's even stronger. Strong bonds inside, and then there are weak bonds with other oxygen molecules. So this characterizes what we call the simple molecular structure in covalent bonding. It's that you have strong bonds within the molecules themselves and weak bonds outside of the molecules. So because of this structure, we can deduce several properties of simple molecular compounds. We can say that they have a low melting and boiling points because of the weak attraction between the molecules. And we saw that they don't have a net charge because once they're together, they're neutral, because I started with 6, for example, for the oxygen I started with 6 electrons here, 6 electrons here, and there's still 6 on this side, 6 on this side. There's still a total of 12 electrons in the whole system. So no electrons got lost or gained by this system of 2 oxygens. So there's no net change in the charge. They were neutral to begin with, and they are still neutral, so there's no net charge between them. Hence they don't conduct electricity, because in order to conduct electricity, you need charges to flow. And finally, we see that they don't dissolve in water for the same reason. In order to dissolve in water, they need to have some charge. We've not gone into the notion of solubility yet, but we will look at that later. So for the moment, don't worry about this last point here, dissolving in water. So we see there are quite a number of differences between molecular compounds and ionic compounds. It's quite the opposite. In ionic compounds, we have really strong bonds between the ions, so ionic compounds have very high melting and boiling points. And ionic compounds, being ions, they have net charges, so they can conduct electricity and dissolve in water. So next we'll take a look at a different variety of covalent bonding, one where many atoms join together to form a giant structure.